Isotropy or anisotropy. Analyzing the semivariogram in different directions.
The first thing that we are going to do is analyze the experimental semivariogram in 4 different directions. Then we are going to use the script number 18. Is this one over here, and this one is the directional experimental semivariogram for the first order trend surface. And remember that if you want to implement this script in your QGIS, you can watch the lesson 4 of the 3rd geostatistics course. In this case, we are going to do the analysis for isotropy or anisotropy just for the first order trend surface, because that's the model that we are going to use for the Kriging interpolation. But remember that if you want to do the analysis for the second order trend surface, what you need to do is just edit this script and change the formula over here for a second order trend surface. Now we are going to fill all these parameters. The layer is going to be this one, the one we remove the outlier, could be any of these two. Then the dependent parameter is going to be the groundwater. The independent parameter is going to be X and Y. The cutoff at the beginning, we can use all the extension to have a general view, right, of all the experimental semivarograms in all directions. But remember that as we are using now a directional one, the lag distance, each point for the lag distance is going to be with less pair of samples. Then we have to assume that the experimental semivarograms are going to be pretty weak, okay? Then in this case, the total extension is 450,000. The tolerance angle is going to be 22.5. Remember, if you don't know about these parameters, you can watch the 4th lesson of the 3rd geostatistics course. Then the lag distance is going to be 45,000. Is the lag distance, is the cutoff divided by 10, okay? Then the first direction is going to be 0 degrees. The second direction is going to be 45 degrees. The third direction is going to be 90 degrees. And the last direction is going to be 135 degrees. With this configuration of the angles, we are going to have coverage of all the area, and the bins are not going to overlap, okay? Then we are going to fill this information here, but I'm going to pass the video faster. Okay, I added this information. For X is going to be the lag distance in meters. For Y is going to be the semi-variance for the groundwater elevation in meters. Title of the graph is going to be experimental semi-variogram in 0, 45, 90, and 135 degrees. And the subtitle is going to be raw data. Then we can run this script. And double click to open. Let's go to make this screen bigger. The question here is there any direction where the semi-variance is very low compared with the other directions? If the answer is yes, in that case we have anisotropy. If the answer is not, then we have isotropy. And in this case, as you can see, the correlated area, that one is the most important one, all the directions are showing approximately the same semi-variance. Then in this case, we have a clear example of isotropy. Later, we are going to do the same graph, but just for the correlated area and with a small lag distance. Then in that case, we can be focused in this area of the graph. But before to do that one, I prefer to do this one, you know, with all the extension, to have a general view of all directions, to see if there is anything wrong or anything that is pretty weird, but it's not the case, right? The next step is to do the variography, and also again, I'm going to do the variography for all the extension. The script for the variography is going to be the number 30. Number 30 is this one over here, and it's going to be the script variography for the first order trend surface. Remember that if you want to implement this script in your QGIS, you can watch the lesson 6 of the third geostatistics course. Then in this case, we are going to select this or this one, it doesn't matter. Then again, the dependent parameter is going to be the groundwater. The independent parameters are going to be X and Y. The cutoff, as I said, is going to be all the extension, then it's going to be 450,000. The lag distance is going to be the cutoff divided by 10, then it's going to be 45,000. Now I'm going to copy and paste these ones over here. Then this one is going to be the lag distance. Oh, maybe I can put something different here. For X, I'm going to add the direction east west. For Y, I'm going to add north south. Title of the graph is going to be variogram map. Also could be variography, right? But it's better known as a variogram map. Then for the subtitle is going to be raw data. And for the legend title is going to be semivariance. Then we can run this script. Let me put here on the top of this one, then run. And double click to open. Let's go to make this screen bigger. And as you can see in this map, we cannot see any specific direction, right? What we want to see, for example, if we have anisotropy, is a low semivariance in one specific direction, but it's not this case. We don't have any specific direction on the map. Remember that the variogram map is the representation, is the graphical representation of the experimental semivariogram. But in the variogram map, we can see all the directions, right? Here, we have the representation of just 4 directions, 0, 45, 90, and 135. But here we have from 0 to 180, all the directions, right? For 0 degrees is going to be this direction. For 45 degrees is going to be this direction. For 90 degrees is going to be this direction. And for 135 is going to be this direction. And that information is the same as we can see over here, right? In each of these directions. Now we are going to do the same, but being focused on the correlated area. Then first we are going to go here, take this one, and we are going to do the same. But in this case, what we are going to add here is just 150,000. And also here for the lag distance, 15,000. In this way, we are going to have more lag data points, you know, for the lag distance at the correlated area. Double click to open, and let's go to make this screen bigger. Again, in this graph, we cannot see that there is a specific direction where the semivariance it's lower compared with the other directions, right? In general, these 4 directions, they are showing the same semivariance in all the correlated area. That is indicating that our data is isotropy. Then we can do the same, but now for the variography. Then we are going to take this one, variography, and put here 150,000 and 15,000. Then run. Double click to open. And again, as you can see here, we cannot see any specific direction. You know, it's very clear that the data is isotropy because you cannot see any direction in this variogram map. Then as a conclusion, we can say that our data is isotropy. Then in this case, we don't need to work with any type of experimental semivariogram in one specific direction to do the Kriging interpolation. What we are going to do is just the Kriging interpolation, assuming that our data is isotropic, and then we can use the omnidirectional experimental semivariogram. Even in that case, the omnidirectional experimental semivariogram is going to be the strongest one because it's the one with the higher number of pair of samples, okay? And that's very important. When we want to work with directional experimental semivariograms, remember that we need to have a lot of data in order to have a strong experimental semivariogram. But in this case, we don't need to work with a specific direction because the data is isotropy. As the data is isotropy, we are comfortable working with the omnidirectional experimental semivariogram. Also, other important thing is to be aware that here, even I put here raw data, now what we are using is the residuals, okay? That it's not the original data, is the residuals. And the residuals is from removing the first order train surface, okay? You have to be aware of that. Maybe you can add this information over here, right? Data from the residuals or just variogram residuals, first order train surface, something like that. But that aspect has to be very clear, right? That this data, these residuals are coming from the first order train surface. Now the next step is to do the Kriging interpolation using the universal Kriging.